Good morning, good afternoon, good evening, or good night. Today, we are going to talk about one of the most critical engineering challenges of our time, access to clean drinking water. The statistics are sobering. The World Health Organization reports that a staggering 2.2 billion people still depend on unsafe drinking water. This isn't just a health crisis, it's a major barrier to economic development, leading to disease and lost productivity in nations across the globe. The problem is only getting worse due to climate change, aging infrastructure, and a growing population, which are outpacing the capacity of conventional water treatment plants. This is why we need to search for innovative and sustainable solutions. Fortunately, the areas with the most severe water stress, like North Africa or the Middle East, are also rich in solar energy. This provides a unique opportunity. This goal is to convert that free solar energy into fresh water using systems with minimal moving parts. To address this challenge, our report reviews three promising technologies that dominate recent mechanical engineering literature. First, we have membrane distillation, or MD. This is a low-pressure thermal process in which a special membrane allows water vapor to pass through but blocks salts. The second technology we'll be discussing is solar interfacial evaporation, or SIE, a newer method that uses a dark absorber to heat only the surface layer of the water, which greatly reduces heat loss. Finally, we'll look at hybrid solar systems. We will then compare these technologies based on their energy efficiency, cost, scalability, and maintenance to determine the best solution for an off-grid village.
In many remote or coastal areas, millions of people still rely on expensive and unsustainable methods like trucking or diesel-powered desalinations to access clean water. The major barrier is the lack of grid electricity, which makes traditional systems like reverse osmosis impractical. At the same time, these regions have often an abundance of solar energy, but current water treatment options waste fuel and emit CO2. Our challenge is to design a low-carbon, low-maintenance desalination system that uses locally sourced solar energy to convert saline or brackish water into clean drinking water. These systems must be reliable, easy to operate, scalable from small villages to town, and cost-effective in the long term.
On this slide, you see three approaches our group is investigating. 1. Membrane distillation. 2. Solar interfacial evaporation. 3. Hybrid PV/RO plants. I'll start by showing you how each methods work in more detail. Membrane distillation relies on a hydrophobic membrane to separate a hot saline feed from a cold distilled side. Because the membrane repels liquid water, only vapor can pass through its pores, driven by the vapor pressure difference between the two sides. A major advantage of MD is that it operates below 100 degrees Celsius, which is near atmospheric pressure, allowing for simpler, safer hardware without using high-pressure pumps. Engineers have come up with four neat upgrades for membrane distillation. 1. 3D printed spacers. These act like little fins in the water channel, stirring things up so heat and steam move faster, no extra power needed. Second, super hydrophobic PTFE sheets. Think of a super slick nano-textured plastic that salt and grime just slide right off, keeping the membrane clean longer. Third, integrated heat recovery loops. Instead of tossing out the warm water you just made, we feed it back into preheat the incoming water, salt water, saving up to 20% of the energy. 4. Modular cassette designed for easy scaling. Each membrane unit is built like a Lego brick. When you need more water, you just add another module and hook it up. Let's rate the strength and limitation of MD. On the plus side, MD tolerates very high salinity what feeds with organic contaminants, and it uses low-pressure PVC or HDPE piping rather than expensive stainless steel. It's also proven in the field deployment across remote sites. However, MD suffers thermal losses across the membrane, which limits overall efficiency. Operators must periodically perform acid cleaning, typically critic or hydrochloric acid to remove scale-up buildup. Finally, while the MD flux rates are competitive, they remain lower than those reverse osmosis, meaning larger membrane areas may be required for the same output. Next, we'll switch gears into solar interfacial evaporation, or SIE. SIE uses a wicks, which is a dark porous absorber that floats at the water's surface. A nanostructure coating, often carbon nanotubes, convert incoming sunlight into heat right at the interface. Because only a thin layer of water is heated, bulk water and container losses are minimized, pushing thermal efficiencies above 80%. Importantly, SIE operates at atmospheric pressure and requires no boilers or large pumps. SIE evaporation is really clever, but a few mechanical issues remain, and engineers have a smart fix for each. 1. Salt management. Tiny grooves in the wick actually shake salt crystals back into the water, so they don't clog the surface. Second, structural support. Aerogol materials are great at trapping heat but can break easily, so we sandwich them in a plastic or wire mesh frame for strength. Third, condensation. A simple clear plastic dome or even a 3D printed channel sits over the wick, Steam heats its cool surface, turns back into water droplets, and drips into a trough below. Fourth, durability testing. Finally, teams are leaving prototypes out in the sun, rain to see how they handle UV exposure and slime buildups. Soaked lab data is one thing, but a real seawater proves the real durability. In summary, SIE delivers remarkable lab-scale efficiencies and ultra-compact footprint with a few moving parts, making it highly attractive for decentralized water production. Yet today, most data are from beaker-scale experiments. Scaling up without sacrificing performance remains the key challenge. Long-term stability under field conditions is still unproven, and the condensation subsystem adds some bulk to the overall unit. Nevertheless, ongoing innovation in material science and model design are steadily closing in.
Hybrid PV RO plants. So here we're talking about systems that mix solar panels with reverse osmosis to make fresh water. What's cool is that they work day and night using batteries, but the downside is that they are a bit more complex and cost more to build and maintain. Here in our diagram, it shows how solar power runs the system and the salty water gets filtered into fresh water. In our second slide, we're going to see the different types of hybrid systems. For our first type, it just uses solar panels and batteries. For the second type, it just adds heat collectors. And for the last type, it includes diesel backups for when there's no sun. Each setup works best in different conditions and different types of environments. Some of our pros is that the system gives water 24/7, use proven tech, and work great for schools and clinics. Our downside or our bad side is that it costs more and is harder to set up and isn't fully green because you use diesel sometimes. So there are trade-offs between reliability and cost.
So let's see how these methods stack up against each other. With membrane distillation, what you have is a reliable, efficient, and simple system that is tolerant to contamination. With the SIE, solar interfacial evaporation, there is high potential, it's very high efficiency, but there's just not enough research and pilot programs to allow for widespread usage. And with PVRO, it is a well-established method, but it just comes with the trade-off of very high maintenance costs because the membrane itself tends to be fragile in high salinity environments. So what are the takeaways from here? Well, membrane distillation is being used widely in off-grid regions, especially because of the simplicity and reliability. That being said, with other methods like SIE, there is a high need for research and more testing and pilot programs to make sure that the performance is as good and reliable in live environments as it is in lab settings. All these methods are really fulfilling the UN's SDGs and pushing the world into a more sustainable and optimal future. Thank you very much for listening. These are our sources.